Hi everyone! Welcome to today's class. I am teacher Nicole and I will be your teacher for today. So for today's class, we are going to talk about something interesting. We're going to talk about nuclear fission and fusion. The things that I feel are most important for you to learn today are the following. First one is you should be able to define nuclear fission and fusion. Second, compare and contrast nuclear fission and fusion. And lastly, you should be able to explain practical uses of the two. Are you ready? Okay, let's start. So a little history of the nuclear fission and fusion. In an atom's nuclei, changes can occur in the structure of an atom. These are called nuclear reactions. In some nuclear reactions, a large amount of energy escapes. This energy is called the nuclear or atomic energy. Most nuclear energy is produced naturally by the sun and stars. But since the early 1940s, man has been able to harness the power of the atom and create man-made nuclear energy. There are two ways to start nuclear reaction. First is fission. The second way is fusion. So a lot of us has already heard of the terms nuclear fission and nuclear fusion before. Nuclear fission means the splitting of atomic nuclei. This is the process by which energy is generated, and guess what? Nuclear power plants. On the other hand, nuclear fusion is exactly the other way around. Here, the atomic nuclei combines. Okay, so one result of the nuclear fusion shines down on us from the sky. This is the energy that the stars, like the sun, emits. So I have a lot of questions, but the first one is, but what exactly happens in these two processes? And why is there so much energy released in the course of time? To be able to understand all this, we first need to have a recap on what does the structure of an atom looks like. Okay? So this is an atom. In the center, that is the atomic nucleus. That is to say, the thing that splits or combines with other atomic nucleus. In the nuclei, it is composed of protons and neutrons. So protons, as you can remember, are positively charged, and neutrons has no charge at all, hence they are neutral. So as a whole, the nuclei is positively charged. So around the positively charged nucleus are electrons, or the so-called electrons, whirring around in a sort of a cloud, and these electrons are negatively charged. So now that we've remembered the structure of an atom, let's see what happens in a nuclear fission. Okay, so a nuclear fission. But first, let us take a look at this illustration. This is what happens during nuclear fission, okay? So, in nuclear fission, the atomic nucleus there at the center is going to get hit by a free-flowing or free-moving neutrons. So, the impact caused the atomic nucleus to split into two separate nuclei. Each one of them will take part of the electrons with them, so that two new atoms are formed. In the case of some larger atoms, a few neutrons are released. When uranium atoms are split in power plants, this usually involves the release of three additional neutrons. This can then affect the fission processes in a chain reaction. Thus, energy is now released, and very much of it at that. How much energy, you may ask? Well, 1 kilogram of naturally occurring uranium has the energy equal to 12,000 liters of mineral oil and over 19,000 kilograms of hard coal. Because we get energy from either oil or fossil fuels, or the splitting of atoms. So if you can compare, there's a huge difference between the kilogram of uranium and oil and hard coal. Let us now talk about nuclear fusion. What is nuclear fusion? So basically, nuclear fusion is when two or more very light nuclei moving at very high speed are fused together to form a single nucleus. Then the process is known as nuclear fusion. So unlike the nuclear fission, which is dividing one atomic nucleus, here in nuclear fusion, it is the combining of two. Okay? So fission, dividing, fusion, combining. Fusion is exactly what it sounds like, the fusing of two atoms together. Due to the internal forces acting on the nucleus, this reaction cannot be obtained just by applying pressure on the atoms. It takes not only an incredible amount of pressure, but an immense temperature. That is why it happens in the sun, in the star, where there is extreme temperature. Okay? For us to be able to combine the two atoms. Fusion only works with smaller atoms like hydrogen and helium. So it is the process by which multiple nuclei join together to form heavier nucleus. So it is accompanied by the release or absorption of energy depending on the masses of the nuclei involved. Fusion is being examined as an alternative energy source on Earth. Nuclear fusion of hydrogen to form helium occurs naturally in the sun and other stars. It takes place only at extreme high temperature. That explains why the sun is an endless source of energy. Fusion can be used in good or evil way, okay? So good one is a controlled reaction in a reactor used to produce cleaner and inexpensive electricity. For evil, a fission bomb starts a fusion chain reaction to create an incredibly powerful weapon. Thermonuclear weapons such as hydrogen bombs, much more destructive than the atomic bombs. So now, let us talk about why is there a need to further venture into fusion research. It is one, because of the ever-increasing energy demand, limited fossil fuels. Third is global climate change. Fourth, limited scope of renewable energy. And then with fusion, there's high energy output. Okay, so we've covered much already about nuclear fission and fusion, and I hope everything is clear as of now. And at this moment, I would like to share to you what are the differences of the two. Is there any difference, or is there any common thing between nuclear fission and fusion? So in the following slides, I will give to you the comparison. Okay, let's check. Okay, so we will talk about fission versus fusion. So the difference. So these are two physical processes that produce energy from atoms. The first one with fission, again from the name itself, fission, it splits a larger atom into two or more smaller ones. Splits larger atom into two or more smaller ones. With the case of fusion, fusion joins two or more lighter atoms into a larger one. That's why I'll talk to you before that it only happens in small atoms or the smaller ones. The second one is, okay, let's talk about the fuel type. So with fission, we have uranium, plutonium. With fusion, we have hydrogen. With the byproducts, in fission, use nuclear fuel. With helium, with fusion, it's helium. Okay. Then in terms of uses, fission is used in energy production, and then for fusion, it's under development, but still, in the researches, it's the cleanest, okay? With the energy, fission, let's compare, fission is 1 million times greater than other energy resources. But take note, fusion is 3 or 4 times greater than fission. So in conclusion, nuclear power is a double-edged sword since it can bring both disaster as well as life. It only all depends on how we use it. Because as we can all remember, nuclear power can be used as a very efficient and high output energy source. But it can also be very dangerous because it can be used as weapons, bombs, and other machineries. Okay, so it depends on how we use it. Okay, so here we have disaster and life. Sun as being the giver of life here on earth, we depend on the sun, and disaster because whatever good things here on earth, if it is used in a bad way, it will give bad results to everyone. So to further add up to the learnings, I will show to you a video later on about the atomic bombs and the hydrogen bombs and the detonation. So it will show to you how dangerous it is if used in bad way.
Ever since the first nuclear weapons test in the deserts of New Mexico and the bombings of Hiroshima and Nagasaki, nuclear weapons have become significantly more powerful. Since the first test in New Mexico by the United States in 1945, 2,475 nuclear weapons have been detonated across the globe. Over 85% of those detonations have come from only two countries, however, the United States and the former Soviet Union. Only 2 of those thousands of detonations were ever used in a war, the ones dropped on Hiroshima and Nagasaki during World War II by the United States. But those bombs were very small compared to modern weaponry. The Hiroshima bomb produced an explosion of 15 kilotons, or 15,000 tons worth of TNT. The bomb dropped on Nagasaki had an explosion of 21 kilotons, but how much bigger can nuclear weapons possibly get? The answer is, terrifyingly, much, much bigger. The largest nuclear weapon currently in the United States arsenal is the B-83, which can produce a blast of 1.2 megatons. To understand the scale from here out, 1 megaton is equal to 1 million tons of TNT, and that is equal to 1,000 kilotons. Remember that the Hiroshima blast was just 15 kilotons, so that means that the B-83 produces a blast 80 times more powerful than that. What I've been showing on this scale is only the size of the mushroom cloud that the bombs produced, so to further add to the scale, we're going to place the size of Mount Everest here and the average altitude of a commercial airliner that you would normally fly on here. So, the Castle Bravo bomb is the largest nuclear weapon ever tested by the United States. It produced a blast of 15 megatons, or about 1,000 times the scale of Hiroshima. But even that pales in comparison to the largest nuclear weapon ever detonated. In October 1961, the Soviet Union created the largest man-made explosion ever in human history when they detonated this device, known as the Tsar Bomba, here over this territory known as Novaya Zemlya. The bomb detonated with an astounding force of 50 megatons, or about 3,333 Hiroshima blasts. It was so powerful that it almost destroyed the plane that dropped it, shattered windows as far away as Norway and Finland, and the shock waves created by the bomb circled around the entire Earth 3 times. But this test was actually just a scaled-down version of what was theoretically possible. Although never tested, the Soviets did have plans to create a bomb that would be twice as powerful as even the Tsar Bomba, a bomb so powerful that it would have produced a mind-boggling 100 megaton blast, or about 6,666 Hiroshima blasts altogether. To get another sense of scale, let's imagine that Times Square in New York City would be the epicenter of these blasts. You can test this stuff out yourself on the website NukeMap after watching this video. I'll provide a link for it after the end, but let's see the results first. First off, we're going to show the size of this detonation, which was caused by the recent North Korean test in 2013. Following this, here's the size of the Hiroshima detonation, which isn't really that much bigger, but let's move on to the B-83 bomb that we were talking about. As you can see, it would affect a much larger area than the Hiroshima bomb. But moving on past that to the Castle Bravo test, we can see how it truly dwarfs everything before it. But even that blast is incredibly tiny when we move on towards the Tsar Bomba as seen here. And then finally for our scale, we move on to how large the blast from the theoretical 100 megaton version of the Tsar Bomba would be. The blast would be so powerful, this is what the blast radius would look like if you were observing it from the International Space Station. So the question then becomes, should any of this really worry you? How many nuclear weapons exist today anyway? Well, in total, there are estimated to be around 15,600 nuclear weapons in the world currently, enough to destroy the entire planet dozens of times over. But only 9 countries control that stockpile, and 92% of those weapons are controlled by only the United States and Russia. The other 8% of the global nuclear arsenal is controlled in descending order of numbers by France, China, the United Kingdom, Pakistan, India, Israel, and North Korea. Israel is, however, highly secretive about its nuclear program and has never publicly confirmed nor denied the existence of their nukes. It's just one of those things where everybody knows that they have them, but nobody really comes out and says so. Unless your name happens to be Mordecai Vanunu, a man who did reveal details about Israel's nuclear program and spent 18 years in prison, including over 11 years in solitary confinement. Also interesting to note, South Africa used to be in possession of 6 nuclear weapons because the past apartheid regime was afraid of the 79% of the population that couldn't vote and communists trying to overthrow their government, but they eventually agreed to dismantle all of them, which makes South Africa the only country to ever acquire nuclear weapons and then voluntarily get rid of them. Well, unless you don't count Ukraine, Belarus, or Kazakhstan, which all had nuclear weapons for a brief amount of time after they declared their independence from the Soviet Union in 1991. Ukraine is particularly awkward because after their independence they found themselves in possession of over 5,000 nuclear weapons, which would make Ukraine for a brief period the world's 3rd largest nuclear power and probably one of the most powerful countries on Earth as a result. They agreed to hand them all over to Russia in exchange for a super serious promise that nobody would violate their territory or borders in the future, and we all know how that turned out. As a result of that happening, it's doubtful that other countries would be thrilled to ever give up their nuclear weapons in the future, but leave your thoughts and comments below about how you feel one way or the other. I'd also like if you posted any questions that you have to ask about me personally. My channel recently surpassed 100,000 subscribers, and I'll be doing a short Q&A video about myself very shortly. I'll try my best to answer every question in that video, so if you're interested in that and more content just like this video in the future, I hope that you'll subscribe to my channel by clicking the link here, and you can check out some of my other videos that I've posted over here on the left. As always everybody, thank you all for watching and we'll see you all next time.